don't they? I'm not quite sure why the original decision for that was made, but there is a bit of history there, because that system is an old system now, quite an old system, the VHF ground-to-air system. And probably in the days when it was first invented, shall we say, they decided that perhaps they needed narrower channels, even though they were working at VHF. Because when you're communicating with an aircraft, the range that the aircraft has is much greater than it is on the ground. Remember the little formula we had for the range of radio transmissions at VHF and UHF and microwaves? Yes, wasn't it 3750 times the root of the height, wasn't it? The TX height and also the RX height. Now, if we just look at the TX height alone for a moment, an aircraft flies at about 30,000 feet, isn't it, on its cruising altitude. So we can say that's about 10,000 meters, 10 kilometers. So it'll be 3750 times the root of 10,000, say. Now the root of 10,000 is, don't need a calculator, 100, yes. 4 zeros, root of that 2 zeros, isn't it? So it's 3750 times 100, which of course gives us 375 kilometers, doesn't it?
3570.
Is it 357? I couldn't remember, sorry. It might be 357. Okay, thank you for the correction. Anyway, you understand the point I'm trying to make here. So we're talking about over 300 kilometers at least range for an aircraft. Now, because it's such a wide range, there's probably a better chance of interference with other aircraft. So that's the reason, perhaps, to answer your question about why they used amplitude modulation, in that particular circumstance. But I'm just guessing a little bit there as to the reason, but that could be a reason. You've got a much wider, you see what's happening, of course, in the aircraft. Because the aircraft's flying so high, it has a much wider range, a much greater range, you see. Right. And then, of course, you've got the height of the antenna that you're communicating with, which is only going to be about a few meters, but nevertheless, it gives you a much greater range for the aircraft. Okay, so remember the two types of modulation and why we use each type, the advantages and disadvantages of using, particularly when you're comparing FM with AM. Even if you don't consider single sideband, just comparing FM with AM. AM has the narrower bandwidth, FM the wider bandwidth, but the FM signal has a better signal to noise ratio, less noise. Just think about FM broadcasts and the quality of the broadcast compared to AM broadcasts, radio broadcasts. Should be. And usually when you lose an FM signal, it goes pretty quickly. With an AM signal, it just tends to get more and more noisy until eventually you lose it. Very similar. It's funny you should say that. It is similar. It isn't digital, of course. Don't make that mistake. But it is in the way it sort of disappears. It tends to go quicker than it would be with an AM signal. For that reason. But yes, it is clearer than AM. That's the thing. Transmitter and a typical receiver. That's all. Very simple. I'm not going to go into the details of super heterodyne receivers or anything like that. That's pure radio. But we just need to have a little idea on basically how a radio transmitter and receiver works. What do we need in a transmitter, do you think? Okay, well, it depends on the type of transmitter, but in our case, let's assume we're using it for radio telephony. So we need a microphone. I'll draw a little symbol of a microphone here. Now, what do you think comes after the microphone? Yeah, well, before we get to the carrier, let's amplify, because the signal in the microphone is going to be very small, isn't it?
Yeah.
So we need to amplify it a bit. And the amplifier we use, I'll just draw the symbol here, but of course it's an audio amplifier, isn't it? Meaning it's designed to amplify audio frequencies, not radio frequencies. Okay, let's take the output of that. Now, what else do we need? Carrier. Yeah, remember yesterday we needed to generate a radio frequency of some value, depending on what range and what channel we wish to transmit on, for example. Now, you can draw the symbol for an oscillator like this. You can think of that as a generator, but the frequency which it generates would be the carrier frequency. Okay? I'll just draw a single output from here and put FC there, meaning the carrier frequency. Now, somehow we've got to mix these two together. And the type of mixer we use is called a modulator, isn't it? Now, what type of modulator depends on what we're going to use it for, whether we're going to use FM or AM or whatever. I'm just going to use the word modulator here, so we don't have to commit ourselves as to whether it's AM or FM or whatever it is. Now, usually in a modulator, as you radio guys will learn when you do more on radio, you generate a lot of frequencies, not only the frequencies you wish to transmit, but you could be generating frequencies outside there. So we always follow a modulator with some type, that's right, some type of bandpass filter. Actually, what I'm going to do here, I'm going to give you a little symbol which you might... I'll write bandpass filter over it. We'll come back to why we use this in a minute. Bandpass filter. And sometimes the symbol for a bandpass filter is like this. Can you see that? 3 waves, the top wave and the bottom wave have got a cross through it. It's like we're passing just the middle frequencies of something. Now, we haven't given any values here, but you can see, if I was, say, using a frequency modulator, I would need a bandpass filter, because in a frequency modulator you produce a wide range of frequencies. You want to just restrict that to a certain range, minimum range. Yes, that, and you'd use a bandpass filter for that reason. We would also need a bandpass filter, of course, if we wanted a single sideband transmitter, wouldn't we? Yes, to select either the upper or the lower sideband. Yeah. Now, this is putting it very simply, of course, but you understand why we need these things. Sometimes the symbol for a mixer, incidentally, is this. Right. You might see that sometimes on a diagram. Some of these symbols that change a little bit from diagram to diagram. But anyway, this is our carrier, FC, and our modulator. Then we have some type of filter. Now,
the band stop filter is 3 and 1.
Yes, I think a band stop filter would be, the middle one would be, you still have the 3 waves, but the middle one would be crossed. I'm not so sure this is a universal standard, but it's quite common. It's a common way of showing the filters. You will see it in some diagrams. Again, you see, we're not actually going into the circuits involved here, just basically what each block does. And when you're fault finding, indeed, you start at this sort of level. If you want to find out what's wrong with your transmitter, you test for your signal at different points here to find out which part of the circuit is working and which is not. Okay? Director? Okay. Now, what do you think comes after this? Do you think? What do we need here? Sorry, a antenna? Yeah, maybe an amplifier, Mike, because usually all this is done at quite a low power, low signal level, so as not to interfere, to keep everything, maybe only a few milliwatts or microwatts of power are involved here. So what we would have after this would be some type of amplifier, but of course a special amplifier, not just your everyday amplifier. an amplifier which is designed for RF, and depending on the frequency range. So we'll call that an RF power amplifier, because this is where we want the higher power to be transmitted. Don't forget, this is for telephony, radio telephony. We're not talking about any special use of telephony. And then after that, then we come to the antenna, and the symbol for an antenna is that. That's a universally accepted symbol. So I'll just write here antenna. What type of antenna? Well, that depends on what you're using this system for. If it's mobile, it could be a dipole or a stacked array or collinear array to get all around communication. If it's a handheld radio that you're talking about here, it could be a single dipole if it's at UHF, sticking out of the radio at the top.
So the antenna sometimes it comes close from the top.
You mean there's a line across the top here? Yes, sometimes there is, that's true. You can see this in different... Sorry? Well, I'm not quite sure. I was looking in here, and this they seem to use a lot of. I'll draw both just, as an alternative symbol for an antenna. You might see, is it this sort of thing you're talking about, like that, where there's a line across the top here? In the old days, when this symbol was first thought about, they said, okay, a transmitter antenna will be like this, and a receiver antenna will be like that. Can you see the difference?
Yes.
But this one eventually disappeared. They decided, oh, well, let's just have a common symbol for the antenna, you see. That's how it originated, that sort of symbol. Sometimes you will see a line across the top here, like this. As to which is the most common, I really don't know. It depends on the circuit. But you should be able to recognize either of them as being an antenna. Okay, so that basically is our transmitter, doesn't it?
What the advantage the RF bar?
Well, don't forget, what we've done here, and this is something which you must understand, all these circuits here are all low power circuits.
Yeah.
We're talking about small transistor circuits, maybe integrated circuits.
Yes.
So the power level here, if you were to measure the power level out here, is only going to be small.
Small.
Yes, maybe a few milliwatts. Now, of course, that might not be, in fact, probably won't be satisfactory for transmission. Even in a walkie-talkie, we'd need 3 or 4 watts, perhaps, depending on the system out here. So we need an amplifier to amplify a power amplifier, which means the power output is much bigger than the power
Bigger
input.
the power.
Yes, maybe a push-pull, depends on the system. But anyway, it would be a power. These amplifiers are specially designed to amplify radio frequencies. Okay. Yes. We haven't done the circuits for this, so don't worry about it. We've only done circuits for basic amplifiers, haven't we? Common emitter, common collector, common base, etc. And we've also touched on a push-pull, but the exact design of that amplifier, well, that's a specially designed case. And would have a power transistor probably in it, mounted on a heat sink.
It make the big the
Power. So that what we're connecting to the antenna is a large power compared to this. That's all it does, really. Now, the amplifier would be what we call a broadband, so that it amplifies all the frequencies that are supplied to it from the filter. It's not just one frequency, there's a range of frequencies, isn't there, if we modulate. If you were to, looking at this little diagram here, if this diagram was, say, part of a mobile radio system, now in nearly all mobile radio systems there's a capability of changing channels, isn't there? Change from one channel to another. Now, which part of this circuit would you have changed, or would you change, in order to change channels? Yes, you would switch in a different oscillator, or at least a different frequency determining component in the oscillator. I'm going to come back to this. This is an important point. Up to now, what we've talked about, what do you think we would use here? Or what could be used here? Tuned circuit. Yeah. Well, I haven't mentioned the crystal yet, but a tuned circuit. I'm going to mention the crystal this morning. That's the reason why I mentioned this. So this oscillator might have a switch associated with it, which enables you to switch different tuned circuits. Each tuned circuit oscillates at a slightly different frequency within the band you want to transfer, either VHF or UHF, whatever. So that could be one solution. However, what did we say about these oscillators? Well, first of all, the value of L and C have to be chosen to give you the right frequency, don't they? Carrier frequency. We said actually it's 1 over 2 pi times the root of LC. There's also something else I mentioned, which was the Q factor, which was actually equal to XL over R. Now, the Q factor is important because if these circuits were used as filters, if they were used here, for instance, then we'd need, if I had a low value of Q factor, it has a wide, doesn't it? Remember the diagrams we drew yesterday? If I have two waves like that, both of them are the same frequency, which one of these, A or B, has the highest Q factor? B has the highest Q factor, yes, exactly. Now, if you're going to use a tuned circuit as an oscillator circuit, you want a tuned circuit with a very high Q factor. The reason for this is, if you don't, the frequency of oscillation could change a little bit. It's not what we call stable. Now, that's not a good thing, of course, is it? You want your frequency to be exact. Yeah, because the receiver's looking for a particular frequency. It can't be hunting around for you. And of course you could interfere with somebody else if your frequency doesn't remain exact. So if I use a low Q circuit, such as A, right, then the frequency of this oscillator might not be very stable. It could drift a little bit. Slight change in temperature could change the value of the components. But if I use a high Q circuit, narrower circuit, and also use high value, good quality values of L and C, then I'll get a more stable oscillator. So a high Q circuit is necessary. Now, many years ago, they discovered a particular characteristic of a rock called quartz. You've heard of quartz? Quartz is a mineral. You mine it, you dig it out of the ground. It's a mineral. And they found that if they got a small piece of this quartz, I'll draw it quite big here, but it wouldn't necessarily be this big. Like a block of it.
Yes.
Okay. Not very thick, only a thin piece of it. Okay. If they hit that thing, it vibrated. Right? Which is not unusual. A lot of things vibrate when you hit them, don't they? But the thing about quartz is they found that when it vibrated, if they put a little metal strip on one side and a metal strip on the other side, conductors, right, on the other side of the quartz, and they put that, say, to an oscilloscope, connect it to your oscilloscope, they found that when they hit it, the oscilloscope showed sinusoidal wave. Eventually, of course, the vibrations would stop and the wave would die down to zero. Okay? A little bit like, have you heard of a tuning fork?
Yeah.
Yeah. It's like a metal thing like this, isn't it?
Yeah.
With two little rods, and you hit it on the desk, and you can hear like a sound vibration in that case. And then eventually it dies down after the vibrations stop. Well, quartz is very similar. Now, what they found about this, the frequency at which this thing vibrated wasn't a sound wave, but it was in fact radio frequencies, much, much higher than sound waves. And not only that, the thinner they made the quartz, the smaller they made it thinner, they could increase the frequency, make the frequency anything they want, simply by making this quartz thin or thicker. Now, basically, what this quartz was behaving like was like a tuned circuit, an inductor and capacitor in parallel, but with a very, very high Q. Very high Q, and very accurate too. Very accurate. Precise frequencies, depending on the physical size of the quartz. Okay? So if they use this in an oscillator, what the oscillator would do would produce, remember, positive feedback. The positive feedback would enforce the voltage across the crystal and cause the crystal to continue to vibrate. In the very early days of radio, going back now, even before I was born, believe it or not, in the very early days of radio, in order to get these things to work, the operator used to have to hit it. Starts vibrating and then it was off, you see. Of course, nowadays they don't do that, but that's how they work. They actually physically vibrated. You couldn't see the vibration, of course, but they were actually physically vibrating. Another use of quartz, you might wonder how big this signal is that they vibrate at. Well, have you ever seen these gas lighters for lighting the gas, you know?
Yes.
You press them and they hit a crystal and produce a spark. So it can be quite a high voltage that this thing produces. Okay? The ones that are used for radio frequency, however, usually are much lower than that voltage, several thousand volts. But they can produce quite a high voltage. And once they start moving, once they start oscillating, they can keep oscillating by being used in an oscillator to provide positive feedback and therefore oscillate at a very accurate frequency. So in modern radio transmitters, and as we'll see later also in receivers, instead of using inductor capacitor tuned circuits, you might use crystals. These are called crystals. This is the word I want you to remember. The word crystal, of course, is a general word and doesn't necessarily mean quartz. In fact, modern types of oscillators use a different material than quartz, even better than quartz, but that's how it first started, by using quartz.
Okay, quartz crystal or any crystal is vibrating and it's generating.
That's right, yes.
And you hit it more physically.
Yes.
Would you change the frequency?
No, during the time you hit it, at the moment you hit it, you could momentarily change the frequency, but it will soon settle. It's a little bit like, imagine a pendulum, you know, or weight on a long piece of string or a piece of wood. That's free to move. Depending on the length of the string and the weight, it will oscillate at a certain rate, like a swing. Now when you push it, you might momentarily put it out, but eventually it will settle again. Now the point about the crystal is you don't need to keep pushing it. You don't need to keep doing that. What you need to do is connect that, just like a tuned circuit, with an amplifier with positive feedback. And the positive feedback of the amplifier keeps the thing moving. It's like giving it a very small push at the right time. Feedback from the amplifier, such that when the polarity of the voltage in one direction, it enforces that polarity. If you imagine a swing swinging backwards and forwards, when it's going this way, if you give it a little bit of a push further up, and then when it's going this way, give it a bit push this way, it will keep swinging, won't it? Obviously, if it's going that way, don't try and push it back again this way. Yeah? It's got to be in phase, in other words. Very important, the phase. But remember, with positive feedback, it should be in phase. So without drawing the actual circuit diagram here of an oscillator, we can use, the essential point about this little lesson is that we can either use a tuned circuit, an inductor capacitor, or we can use a crystal. And the advantage of a crystal is very accurate, very precise in its frequency won't drift. It'll stay pretty well spot on. So that's one big advantage of it.
Crystal better
Better than a tuned circuit, yes. Better than a tuned circuit. Let's just put down some of the advantages of using the crystal. First of all, we can say generally it's going to be better than using a tuned circuit. And why? Well, let's first of all, because it has a higher Q factor. And also more stable. That means frequency stability. So that's the reason why we would use the crystal. So in our little walkie-talkie, almost certainly in our oscillator, instead of using inductor capacitors, we'd probably use crystals. Of course, these crystals are fixed. Right? You get a crystal, and written on the casing of the crystal will be the frequency at which it oscillates at. Because remember, it depends on how thick the crystal is, the way it's made, the way it's manufactured. So you buy a crystal according to the frequency you wish. You don't have much control, you know. An inductor capacitor, you can actually change the value of L or C to precisely set your frequency. With a crystal, of course, you don't have that. Get a crystal at a certain frequency, whatever it is. But then that's okay, that's no problem. We know what channels we want to transmit on, so we just get the crystals accordingly. This. It's like a capacitor, and it's got this little block in the middle. The reason why it's like a capacitor is because we've got two conductors either side of the crystal to pick up the signal, so it looks a little bit like a capacitor. It's usually how it's made. So this is the crystal. Sometimes they use the word X, T-A-L. You might have seen this on circuit diagrams, meaning a crystal. And then they would have written there the frequency at which it oscillates at, the frequency of the crystal. Remember, that's fixed. It's not tunable, so you get a crystal to operate at a certain frequency.
How can I get different frequency?
In this example here, if you wanted to use your radio on different channels,
No, about crystal, different frequency from crystal.
you need to replace the crystal with a different crystal to get a different frequency, yes. So in this case, instead of switching different tuned circuits, you would switch in different crystals, wouldn't you? Is that not the question?
Hold it.
Crystal, frequency crystal, different frequency crystal.
Yes.
Which type of crystal to reduce different frequency?
What type of crystal?
TX. Depends on the sequence. Sometimes
Well, don't let's go any deeper into any practical. This is just the circuit I've drawn here. I've not shown any multipliers or mixers or anything like that apart from the modulator. Basically, in this diagram, your carrier frequency depends on the frequency of your crystal. If you want to carry a frequency of 99.5 megahertz, you have to get a crystal 99.5 megahertz. And physically, they're quite small, little things. They look a little bit like this, some of them anyway. They're in a metal container to protect them, with a couple of pins sticking out the bottom. And written on the container will be the frequency, whatever it is, stamped on the container. can see clearly what it's going to oscillate at. Okay, there's about so many little things. Some of the early crystals that were used in older transmitters were much bigger than that, quite big crystals. And you could actually physically take the quartz out of the container. And what I used to do, I used to get a sheet of glass with some powder, you know, there's powder for cleaning pans in the sink, scouring powder, like abrasive powder. Get the crystal, a bit of water, and change the frequency by literally, you know, scraping off a little bit of the quartz.
Fraction.
Yeah, so you do a little bit, wash it, put it back in, see what frequency it goes on. So take it out, change it a bit more. And change your channel that way. But those are the old ones. Nowadays you can't remove these things. You might also have seen, of course, in watches. They also use quartz, don't they? Crystals. And the reason is it's a very high accurate frequency, very accurate frequency. What they do is the watch crystal has an oscillator in it. It oscillates, and then what they do is they go through a special circuit which divides that frequency down, right? So to eventually operate the mechanism of the watch, if it's an analog watch, or the digital readout, if it's a digital watch. It's quite accurate. Most watches now use crystals for that accuracy. Okay, so there's our simple transmitter. It shouldn't come as a surprise to you either that sometimes in bandpass filters they could use crystals to give a very nice, accurate, you know, precise bandpass filter that they want. So again, wherever you find inductor capacitors, they could be replaced with crystals if necessary, depending on the circuit.
The cheap one, oscillator, with the crystal.
The 555 timer
Connected with as a circuit.
with the crystal as an oscillator, as an example of an oscillator, yes.
The 555 timer, is it used for high frequency?
Usually not. No, I'm surprised it was. You found that it's usually lower switching, but it was a 555, was it?
I mean integrated circuit which is connected around it with the.
Yeah, but was the integrated circuit a 555?
555 timer, what is our timer?
Probably lower frequency. Maybe a lower. Yeah, I would think you would need a different type of oscillator or a different type of chip. Because crystals are usually radio frequency. You wouldn't find an audio frequency crystal. You're talking about, you know, RF here.
That we use it in the computer.
Yes, also computers use crystals to determine the frequency of the computer. So many megahertz for the oscillator for the microprocessor.
So that it's effectively airplane.
Well, of course, anything, even in a computer, if you've got a crystal oscillator in a computer, which instead of going to, it's not transmitted like this, but of course it's going to time the microprocessor, isn't it? And although it's very, very small power, it can still radiate a certain amount of energy, just like a transmitter. And this is what interferes with things, you see. You've got to be a little bit careful. If you use a computer, sometimes near a television set, you can get interference.
This is because the crystal.
Because of the crystals, yes. It's because of the frequencies generated in the computer. Now remember that if you were to put an oscilloscope here, then you should see a sine wave, shouldn't you?
Yeah.
A single clean, so yes, a clean sine wave. Just one frequency, that's the carrier, no harmonics, nice and clean. If you don't get a clean sine wave, there's something wrong, of course, here. If you get just a single frequency carrier. But if you put your oscilloscope here, of course, you're going to get a more complex, not square necessarily, it's going to be complex because it depends on,
FM or
yeah, depends what you're putting in here. But usually to test your radio, what you would do, you would disconnect this amplifier and connect instead an audio generator. Remember the audio generator we said? And you set that to a certain audio frequency, say 1 kilohertz. Now if you did that, then what you should see here, let's say this is an amplitude modulator. Right? Amplitude modulator, because it's easier to show this. Then you would see, okay, you'd see a wave like that, where this frequency is the same as this, but the rate of modulation, the rate at which it goes up and down, depends on the audio that you're injecting. You see?
The bandpass filter.
after
This is before the bandpass filter.
After the
After the bandpass filter depends on what you're filtering, right? Whether it's an upper sideband or lower sideband, or you might just be accepting all of it, in which case here would be the same as this. But normally when you're testing a receiver, you would disconnect the audio amplifier and inject an audio signal.
if we use crystal and bandpass filter, that we get clear bandpass.
Well,
Like,
I mean, in this very simple circuit, it probably doesn't make a lot of difference. What happens if I use an inductor capacitor here, I'll probably get a bandpass. If I wanted a wide bandpass, then I have to use a low Q circuit, don't I? Remember, wider band, low?
Yes.
But maybe what I really want is not quite this. What I really want is something like this. Can you see the difference?
Yes, like square.
Nice, yes, almost like a square, ideal bandpass. Now, to achieve that, I need quite a complex filter. It can be done with inductor capacitors, but perhaps crystals might do the job better. See, basically using two crystals and join them together in a special circuit to give you, I mean, again, filters is a study on its own. I mean, you can spend a lifetime just studying filters and the design of different types of filters. We don't have that time, but of course, you can understand there's different shapes of, both of these are bandpass, of course,
Yes.
and they both have the same cutoff frequency, more or less, but obviously one is going to be better than the other. That red one would be better than the black. So maybe you would need to use a crystal to give you that sort of shape. Okay, so there's our simple transmitter. And indeed, the walkie-talkies we used to use used to be all like this, with switching crystals. It was the only way. Nowadays we use a different system called the trunking system, which is a modification of this, including digital electronics. It's outside the scope of this course to talk about that. Okay, so you know what a crystal is? You know basically how a transmitter works. Quite simple. Now let's have a look at the receiver. Any questions on this before I remove it? We do like the opposite way round now. We first of all receive our signal. And now the signal that we're going to receive is going to be very small, isn't it? Unlike the transmitter, we're talking about a few microwatts or even less power. Yeah, so we need to amplify that. But not only amplify it, we don't want to just amplify everything that's received by that antenna. We need to amplify it according to a certain frequency. So some sort of bandpass filter again would be needed, where the filter is tuned to the particular carrier that we're wanting to receive over a certain band. So this filter here,
The bandpass should be adjusted.
yes, either that or switch to different carriers. So we would have a switch here to switch in different filters. Okay. Now the amplifier is important because, of course, our signals are so very, very small. We need to make them bigger to be able to use. So this filter would have to be tuned to the carrier frequency that we want to receive. If I want to receive a different channel, that's the guy we need to change, isn't it? to change channels. Everything else can remain more or less the same. What comes after this, do you think? We can use another amplifier, but yeah, basically, to keep it simple, let's say it's a very simple receiver. After the filter, now this filter could be part of this amplifier. Doesn't necessarily come after it. It can be part of the amplifier. The amplifier amplifies at a certain frequency. It's designed for that. So what we need to do after here is demodulate it. Yes, we're going to demodulate. Demodulator. Now, what's going to be the output from a demodulator? What's a demodulator going to do? It's going to give you
The audio.
Yes, it should do. This is the idea. The demodulator takes the modulated RF. Remember, that's what was transmitted. We haven't changed that yet. And then when it goes through the demodulator, what we should get here is the original audio signal.
Sound.
The sound, well, audio. We'll get sound when we put it through a speaker, yes. So here we have the modulated RF. But here we have audio. Now, what type of demodulator depends on what type of modulator we used in the transmitter. If it's an FM modulator, we need an FM demodulator. If it's an AM modulator, we need an AM demodulator. Now, what we would normally do after this is amplify that audio signal with an audio amplifier. Because it needs to go to a speaker, and the power output from this might not be big enough for a speaker. So we audio amplify it and then connect it to our speaker, so we should hear the sound from the... Now, of course, this is the thing here that you would change for different channels. Each channel a different filter or different value. Again, it could be crystal.
Change the frequency.
Yes. Like if the transmitter changes to another channel and you want to still receive him, you need to change this filter to a different channel, don't you? Same bandwidth, he's still receiving the same sort of signal. Okay, if we draw a little frequency spectrum here, we could say this is channel 1, this is channel 2, channel 3, and so on. And of course, remember, either side of the channel we've got a certain band of frequencies that we're transmitting. So like that, this is our...
A different frequency for each channel.
Different carrier frequency for each channel. But the band of frequency is the same. I mean, if it's somebody speaking into a microphone, we're going to get about, if it's AM, this is going to be about 6 or 7 kilohertz. Total bandwidth, and it'll be the same for every one of these, you see. But the only thing that changes is the carrier.
The other frequency, channel 2.
Yeah, what I'm saying is...
Between channel 1 and channel 2.
Yes, if channel 1 was, say, 100 megahertz,
Yeah.
plus and minus 3 kilohertz is the bandwidth,
Yeah.
well, channel 2 might be 101 megahertz, plus and minus 3 kilohertz for that. Same thing.
Yes.
So whereas the transmitter changes its carrier, we need to change this filter.
Mr. Tom, you said the bandwidth is the same on each channel,
More or less, yes.
but with the music more than the voice.
Oh yeah, but don't forget this is telephony. This is an example here. If you're going to use this as a broadcast receiver, then yes, your bandwidth here would have to be wider. So your radio for receiving broadcast transmissions would have a wider filter, a wider bandwidth filter in there. Again, this could be FM or AM. I haven't said either. The type of demodulator we use would determine whether it's going to be FM or AM. If you're trying to receive an AM signal and you use an FM demodulator, you're not going to get much out of it. If you're using an FM signal, you're trying to receive an FM signal, you must use an FM demodulator, because your AM demodulator will not work properly. You'll not get much out of that. So.
Demodulator, can we say as a decoder?
I don't use the word decoder because it can be misleading later. You see, you haven't finished everything you need to know yet, so we're going to use the word decoder for other things, and you could get confused.
Coding and encoding is to give a signal, some kind of pattern to be transmitted with, so no one could take it.
Oh well,
could understand it.
what you described there sounds like more like scrambling. But coding and decoding means but when we do pulse amplitude and pulse code modulation, we talk about coders and decoders. Now, if I use the word decoder here, it can be very confusing later when we talk about that type of a system in digital systems. So I would not use the word coding and decoding.
I mean the idea of
Well, only insofar as if you put some headphones on and connected it here, you wouldn't hear anything.
yes,
Because here it's radio frequencies, isn't it?
but after demodulator.
Here you would hear it, yes, after the demodulator. But I wouldn't use the word decoder actually on a dial because it can mean something different.
So you would use decoder and encoder for digital signals?
Yes, when we talk about PCM, pulse code modulation, we talk about coders and decoders, we call them codecs. And I don't want to get that confused with the demodulator of our system, you see.
You can use a crystal to different.
You're talking about crystals here? Yes, you can. This, again, you see, this is a very simple example of a receiver. For example, if you were receiving an amplitude modulated signal, your demodulator would simply be a diode and a little capacitor. That would be a demodulator. Maybe a resistor here. This is an AM demodulator. How does it work? Very simple. Remember that your wave coming in is like this, isn't it?
Yes. Positive side.
Right, now what we're doing, we're really half-wave rectifying this, aren't we? So a half-wave rectifier. So if we cut off this bottom part here, we end up with, yeah, and then the capacitor charges during these little pulses, so the capacitor voltage goes like this, doesn't it? Now this is the audio. We then can connect that to an audio amplifier, right, and amplify it and get an audio output here. So it's a very simple circuit, very simple. Sometimes it's called a detector. Rather than decoder, you can use the word detector to detect the audio from the. Of course, this only works for envelope full amplitude modulation, not for FM or anything like that, of course, and not for single sideband, but it will work for.
Demodulator to conversion the frequency
Demodulated changes the modulated RF to audio, yes. That's essentially what it's doing. Even this isn't necessary in this course, but it's such a simple circuit to follow, I think no harm in showing you that. Demodulators can get quite complex, of course. If, for instance, if this demodulator was trying to demodulate a single sideband with no carrier, it would be quite complex because we have to have another oscillator here to introduce the carrier. So, you know, you're talking about a more complicated arrangement. But in its simplest, this will work. You can build your own receiver to receive broadcast radios. Actually, it's maybe even possible to do it without these two amplifiers. I've built a receiver just using a diode and some type of filter. You get a little signal out of it if this transmitted signal is very strong. Was the figure I have here for a gain of a Yagi. Remember, a Yagi is directional, isn't it?
Yeah.
So it's going to have a gain bigger than zero. Now they gave here, for television anyway, between 6 dBs, depending on the design of the Yagi and the frequencies you're using it at. For instance, 4 elements, just 4 elements, is 6 dBs. 6 elements, if you add another 2 elements, you get 10 dBs. And if you have 10 elements, you have 13 dBs.
Not linear.
Yeah, it's not linear. So remember in a Yagi you have your dipole, don't you? And then you have a number of directors in front. Depending on how many of these you have, you make it more and more directional. You might also have what they call a reflector at the back. Whether it's a reflector or a director depends on the distance between the dipole and the element. There'll be a different distance here than here. But if you look towards the smaller elements, this is the direction of your Yagi.
I read about 0.15 lambda, the distance.
Well, I can't remember the figure. It could be, yes, an odd number of half cycles, and here would be an even number of half cycles.
And the reflector it will be longer by 5%.
You're talking about the length of the element.
Yes,
Uh-huh.
5 more than 5% comparing to the.
You've gone a lot deeper than we need to do here.
Shorter than the.
It's unusual that you would need to design a Yagi.
Give us our time.
Did I tell you that?
No.
Oh, I was going to say. I suppose if a Yagi breaks, you might need to replace an element, but I don't know about that. So yeah, between the figures here, 3 dBs up to a maximum of 10 dBs gain. Now, of course, this means this one is going to be a lot more directional with a narrower little diagram here of a Yagi. See the polar diagram there? It's a little bit like I drew. I wasn't very good at drawing, but that's direction, this direction. Okay, let's take a break. Is not. Depending on whether it's.
FM, same like this.
No, that's not an FM, that's AM. FM it wouldn't work like that.
Can you explain FM demodulation?
Sorry?
Explain this FM demodulation.
I'm not in this course. I won't.
مقلوب ها هيا شوف
نزل شوية.
ها
No.
What you're asking, what question?
Rosin, I think it is just to make the solder clean.
Yes, what I'm asking is what is the rosin for? Why is the rosin in the middle of the solder? What's that for? What's the function of it?
In the middle of the solder?
Yes.
Remove that.
No. Make the heat from the voltage. It's come to this metal. Make it heater for the heat. You change
No, not really. Not really that.
Remove oxide.
The flux side is what I'm talking about. Yes, they call it rosin. in the middle of the solder, or fluxite, sometimes they call it. The question is, what's it for? Why is it there?
To make it shiny and concave, I think. Solder.
It's to clean. To clean the solder joint. Because when you're soldering, it's important that, well, if you got a PCB and you have a component on the PCB,
اللي تنظف
تشيل اللحاف.
تلاقي حاجات كده حوالين السولدرين كده زي الدهن كده.
this is the PCB, this is your component that's going through the holes of the PCB. And of course, on top of the PCB, you've got a track, a metal track, probably a copper strip.
Yeah.
And the idea is you've got to solder that to this, haven't you?
Yeah.
Now, when you apply solder, what's solder made of, by the way? Carbon?
Carbon.
Not carbon. No.
I'm giving you multiple choice answers here. Plastic?
No.
No.
Oh, that's an easy one. Skin? What's it made of then? Sometimes it's made of skin if you hit the wrong area, and that hurts. Yeah. No. What's it made? What is solder made of? It's made of two metals mixed together. Sorry? Lead and tin. Remember that? Lead and tin. It's a mixture of lead and tin. It's very soft, isn't it? Tin is a metal. Lead is a metal. And by mixing lead and tin, they make solder. Now you can get different ratios of lead and tin. Some gives you a harder, some are more softer. That's a standard ratio for electronics, yes. 60% lead, 40% tin. Okay? Now,
write down the 10.
الورقة اللي عندي موجودة فيها كل شيء.
okay, let me just...
أكمل الصولدر إلى أجيبه بكرة أجيبه.
هذه اللي انا اقول لك تستفيد منها. نطلب منه الحين انه يسوي زي الكورس المصغر عن السولدر.
هذا هو الصولدر اللي بيجيك كله.
يا اخي ما نبغى شيء هذا. غير الشيء تبغى الحق هو الحين ليه ذكر هذا الشيء؟
أنا قاعد أقرضني سألته ما قلت.
لا جيب لنا.
يعني انت اللي سويت.
قلت والله غلطان هو لأنه قال مطلوبة منه يعطي كورس بالسولدر. قال ما في وقت أنا.
ترك.
كنا عنا الكورس كله.
بس هذا هو الكورس كله أنا تتسولدر.
Solder you buy for electronics has the middle of it, the center part of it, has got this soft fluxite. It's a composition. The idea of the fluxite is to clean, because solder will not attach itself to copper or anything else like that unless it's clean, because you get oxygen in between. Oxidized copper. So you should make sure your joints are clean, and the fluxite will help you to clean the joint. To solder properly, to clean the surfaces, which of course you need two surfaces to make a joint, don't you? Surface of, in this case, the surface of the copper strip and the surface of the wire that's going through from the component. Both of those need to be clean. And fluxite helps you to do this. If you didn't have this, you'd have to put it separately. It makes it a bit more difficult. But for electronic work, you usually get the fluxite in the middle of the solder. Now, having a look at the soldering iron, this is the end that gets hot. Now let's consider how you solder a joint. A joint, of course, is where you get two surfaces you want to join together with solder. Treating the solder a bit like a glue, isn't it, in that case? Only for metals, and it's a conductor, of course. First of all, we must make sure our solder iron gets hot enough. Now, the power of the soldering iron depends on the sort of joint you're going to make. Bigger joints require more powerful soldering iron. Generally speaking, the sort of soldering irons we have would be about 40 watts, something like that, for small electronic work. That sort of. Now, what's the first thing you do when you solder?
Put the degree between put the iron on one side of the component and the soldering the other side. Make the iron, the component heat very hot. And put
If I just put this iron now on here,
no, the degree will be
What is the
25,
degree, maybe?
25 degree. The iron.
90.
45 degree you mean?
For the iron to put it in the component.
Okay, well first of all, remember the iron. If I put the iron here, touching this,
Yeah.
On the top.
then the idea is the heat from the iron is supposed to heat this.
Yes.
Now, it might not heat it very well. The first thing you should do with that iron, the very first thing, tin it. You put some solder on it, on the end of it.
What it's solder.
That's right. What happens when you put solder on a hot iron? Smoke comes off it, doesn't it?
Yes.
That smoke comes from the flux side. You put some solder on the iron, it'll smoke. Now, whilst it's smoking, it means you've still got plenty of flux side there. As soon as it stops smoking, get rid of that. That solder's no good to you. You must use it whilst the smoke is still coming off it. Okay? Because the smoke indicates you've still got fluxite there. But slowly, because of the heat, the fluxite is evaporating. There's smoke. So, you put some solder on. Whilst it's still smoking, you then connect your iron here at an angle. And that solder that you have here will contact both the strip and the wire. And that'll transfer the heat to the strip and the wire quickly.
In the tip, after that, we will the sponge finish to make it more efficiency.
Sorry? Yes, what you're doing, you're putting a bit of solder on to make it more efficient in getting the heat there quickly.
Before of that, I have to clean it.
Well, yes, you tin it and clean it, yeah.
Then I try it.
But you must put the solder on first.
Before.
Yes, and while it's still smoking, put it on the joint. Now you can add more solder to this side here, because now all around here will be hot. Because of this little bit of solder will help to get the heat quickly to these surfaces. You add a bit of solder here, and the idea is to build up a solder joint like this. To be the surface of the joint should be shiny, right, and you should see a nice joint there. And of course, when you take your iron away, let it cool a little, and it should be a good, solid joint.
Before we have to remove the solder before the solder iron.
No, you remove both of them. I mean, at the same time. As soon as you put your iron there first, with the smoke still coming, you then put your solder. It's done. Take them both off. It's done within a second. If it takes longer than that, you didn't have a good enough joint.
Sometimes I have read about it's like remove the solder before the solder iron. Then it means seconds.
Fractions of a second, if that's the case. Yes, you might have to remove the solder first, because if you remove the iron and leave the solder, it might get stuck to the joint. But we assume that you would do that, yes.
يعني تكون تحطها من جنب.
And then after you've done that, you cut off the thing. Okay.
What about if you have multi-line board?
Just got to be more careful. If it's a multi-layer board, it means you've got several layers of printed circuit board. the main thing to watch out there is make sure your soldering iron isn't too hot, or it could damage the board because you've only got a thin strip between each. And usually in a multi-layer board, what happens is a particular layer will have a contact through what is called an eye hole. That will be a tinned connection to the middle board, wherever that is. So you've got to make sure that you... But of course, also what's involved in soldering is how to solder and unsolder surface-mounted components. That's another thing that you might need. Remember our microprocessors? They have hundreds of connections all the way round, very fine wires. On the older ones, or some of the logic circuits, they need to be soldered flat onto the board. They're flat, they don't go through holes, they're flat soldered. The way to do that is to use solder paste, a bit like toothpaste. Put the paste on here, like a toothpaste, you know the toothpaste? Paste onto the, all of them. And that's got solder and fluxide in it. And then you just rub your irons across here like this. The solder will congeal around the contacts, and that's how you make your solder connections.
What about if one by one?
No, you don't do it one by one. Just do it like that. One by one is very difficult.
You can damage.
You've got to be quick. You've got to be very quick, because don't forget, these things can be affected by heat, so you don't want to put your soldering iron on too long. So you go quickly through it like that. This is a technique. You're not expected to do this straight away. You've got to practice it a little bit. You run it slowly along like that, and it solders each one in turn.
The computer does it faster than you. The computer always
Yeah, usually these things are put onto boards in the manufacturer automatically by machines. It's only if you need to replace a component. If you had an integrated circuit chip on a board with just a few connections around each side, and you need to remove that from the board, how do you remove it?
Which one?
An integrated circuit like this, not this one, not surface mount.
It depends on
It depends on to move the solder.
So what you're going to do is, let's say it's here, let's say this is part of it, you would heat Is that the best way, do you think?
Strip it, take it off.
The easiest way to remove, assuming this is faulty,
It's fault for the
It's
base.
faulty?
Put the base for it.
I'm sure it is.
and you want to remove it,
I will cut it. But
yeah, you cut all these pins first
Put the base.
with a pair of cutters, take this thing off, and then using a pair of pliers you remove each of these pins in turn, one at a time. Don't try and unsolder the whole thing unless it's a good one that you need to take off.
Another idea to take it off of the cut and put the base for it.
Uh-huh.
Take it off.
Well, there's also certain tools you can use. There are certain tools you can use. Like unsoldering tools that will help you.
That's
Take
all
it off.
I'm saying. To put for the chip here, base for it. You know, some base for the chip to put it, or to take it
A
directly.
socket, a socket.
Socket.
Oh, a socket.
Socket, yeah.
Oh, yes, a socket, yeah.
It's better than cut.
Yes, it is. If you're going to have to remove chips, obviously a socket can save you a lot of problems, because you just solder your socket into place and then you just unplug your chips when you need to. That's right.
For the surface mounted.
We have some videos, you know, on this.
They use hot air.
Sometimes hot air. Yes, same with yes. Sometimes they use hot air instead of a soldering iron, and they blow hot air, very hot air, of course, onto this paste, and it causes it to solder. And when you come to take this off, if you need to unsolder that,
Hot air.
you can use, but another way, assuming this is a faulty one and you want to get rid of it, you can use a knife to cut all your pins off. A sharp knife, because they're only thin pins, and then remove the chip, and then you can remove these separately without damaging them.
what is that kind of tooth? You melt it or
The paste,
Paste.
soldering paste, soldering
Don't cut
paste.
it like this, because you go down on the board.
Well, cutting just the things. Yeah.
Yeah, but you see,
Making sure you don't damage the board. Yeah.
there's a company in Riyadh called AEC, Advanced Electronics Company. I worked over there for a while.
Uh-huh.
There are some people who went to the USA for only soldering,
Yeah.
and they are more than professional. If they want to cut, they won't cut like this. They have to cut like this.
Yes. Yes. Using the blade, not the tip.
They are
Yes.
not using the blade, and they're not going like this on the printed board. They're going like this on the components.
Uh-huh. Yes. Okay. We have some videos actually showing this. How often you would need to do this sort of soldering, I'm not quite sure.
Very like,
I didn't find that.
sometimes there are some IC ships that are very small. There's some printed boards.
Yeah.
They are not
Soldering.
mounted like this one with
Desoldering
bolts.
Yeah.
The surface mount.
Surface mounted. Yeah, that's what I was talking about here, surface mounted.
It's not only microprocessors, some small other chips.
Yes, oh yes. You can get surface mounted components in any. And usually though, these boards that contain this, if something goes wrong with them, usually tend to replace the whole board rather than mess around with the individual chip.
But you know, I didn't find that.
عرفت تجي
You didn't find
That video.
the video? Yeah, you were looking for the video, weren't you? No. I know it was a few years ago since I last saw it. I don't know what's happened to it.
Yes.
The flux is to clean the surface.
Yes, to clean. When you get a clean surface, right?
Isn't it to help the lead to melt?
No, it isn't. The flux itself is to clean the surface. Now, when you get the surface clean, then you get a better contact between the lead, or the lead and tin, and the surface. And that helps to transfer the heat. But it's because you're cleaning the surface that helps transfer the heat.
But you use flux by alcohol.
Well, you shouldn't have that much flux, actually. Remember, in the flux that's in the middle of the solder, it's continually evaporating as smoke.
No, but sometimes you need, there is this flux liquid you have to put sometimes to get.
Yes, if you use too much, then you might get when you finish the soldering joint, on the outside of the solder, sometimes you get a little blob of flux.
Yeah.
It's like a brown stain,
And
on
that's
your
very
solder
dangerous
joint.
one.
and then you might need to use some spirit or something to get rid of that.
Alcohol, actually, you-
Alcohol will do it. Yes.
Because this one, after a period of time, would do a corrosion on the.
It will do, yes. You've got to get rid of that sort of thing. If you have that much flux. The idea, of course, is not to have to, not to overdo it on flux, but using the right type of solder, you should be okay.
في ناس عندها أزمة ريحة الفلكس هي شمونة هذا الدخان والله الكلية
سام الجو سام
نحطه في الفلكس ويجيب
يجيب لك حساسية على طول.
سرطان ايه راحت ايام.
I was reading through the notes on BUT. Let's just do these two topics in telecoms. The first topic is a different type of multiplexing called time division multiplexing. We need to have an idea what this means. Time division multiplexing, or you can just say TDM. And we need to know the difference between this and frequency division multiplexing, which is the different type of multiplexing.
FDM?
Yes. Now, we've already talked about FDM when we talked about radio communications, where you have a different channel separated from each other channel. That's frequency division multiplexing. Each channel occupies a different bandwidth. Okay. Time division multiplexing works in a slightly different way.
Different bandwidth and the same frequency.
No.
Frequency division multiplexing, are you talking about, uses a different frequency, right, for each channel. Different carrier frequency. Right? Remember, in frequency division multiplex, in FDM, if this is your frequency spectrum, then each channel is separated from its channel next to it, like this.
Separated the bandwidth.
Yes, along the band. Each of this is a different carrier.
Different kind.
The width depends on what you're using it for, but if it's a telephone channel, that's about 6 or 7 kilohertz, isn't it? Each one. That's FDM.
But the frequency will be different.
The carrier frequencies, yes. This is frequency here, you see, you're plotting
Yes.
each different carrier frequency.
Different.
Okay, that's the normal FDM that we're used to in radio communication systems. Now let's have a look at TDM, which is a slightly different. I'm going to explain the principles of it by using a little switch here.
أنا نايم والله. لا ما أعرف.
Alright, this shows the principles of TDM. Here I've shown an example of 4-channel TDM switch. Then I'll explain how it works in a minute. What I've got actually in each of these positions is this is like a rotating switch. I've got a position A, B, C, D. Each position has a little microphone attached to it through an amplifier. At the other end, I've got A, B, C, D. Each position has a speaker and a microphone and an amplifier attached to each. Okay, so these are microphones, these are speakers.
Yeah.
And the idea is we're sending information from here to here. And I'll explain now, when you've taken this diagram down, how it works.
It's better to, in time division multiplexing, they use digital signal more than analog.
Yes, that's true, but you can still have time division multiplexing using analog signals as well.
It won't count because it's...
It does. We use it in a system where we record voice on a tape called the word safe. Have you heard of the word safe? Faisal, you know about the word safe, yeah. This uses exactly this principle. Yeah, exactly. Doesn't use digital signals.
Sharing time.
Mm. A lot of TDM does use what we call PCM, but this I'm not. The PCM is a different subject. This is just TDM I'm talking about now.
PCM stands for?
Pulse code modulation. Yeah, that's right. And you can use pulse code modulation in a TDM system, which is very common. But this is a system of TDM which is actually not using digital signals, but it's actually using analog signals. And I'm beginning with this because it's one of the easiest to explain, to start with, if you can understand this, before we go into PCM. And it is actually used. We use this in one of our voice recorders. Okay. Now, as I've drawn it here, I've shown the switch in position A. We can call this, if you wish, we can call this the transmitter part of it, the TX switch, and this is the RX switch, the receiver part. All right. Now, in position A, we have a microphone, right, and an amplifier. Goes down, connected through the switch, through the line here, up through the switch in the receiver to this speaker on channel A. Agreed? Quite simple. Now what happens when I switch to position B? In position B, somebody's speaking here, go down through here, up through here. This is also in position B, and will come out of this speaker. So whoever speaks in that microphone will be heard in this speaker. And the same for position C, will be heard here,
Same channel.
and position D heard here.
Same channel.
Exactly. Well, it's the same, using the same connection here. Now the idea is this. If we rotate this switch, both these switches, fast enough, okay, so as to take a small sample from each of these inputs here in turn, and send it over to the other side here, we do it fast enough, then it's as though we are continuously connecting each of these channels, A to A, B to B, C to C, and so on. And we can show this actually on a diagram. When you speak into a microphone, you produce, of course, audio waves, don't you? I'll just draw a single frequency here to make it simple. And the idea is, if you can sample that wave at a certain instant in time, you'll get a certain voltage. Okay? You send that voltage through the switch to the receiver, and it will be received in your receiving channel. Then the switch moves to the next position, position B. Right, so we've got another person speaking into the microphone. A little bit later, then he samples the voltage here. Slightly different voltage, which is then sent down through the switch to position B. And so on and so forth for C and D, or indeed for any number of channels. I've only drawn 4 here as an example, but you could have more than 4 channels in a practical circuit. Now the idea is, these switches have to rotate fast enough in order to take the samples fast enough. Otherwise you'll get a break in the conversation. The only other thing we need to realise is how fast do these switches need to rotate? Well, remember in telephones, in telephone channels, what we've got to consider is the frequency range. What's the lowest frequency?
300.
That's right. To about 3,600 Hz.
Yes.
Okay. Well, what they say is this. Providing I can read the signal here, right, at least twice in every cycle, then I will reproduce the sound faithfully at the other end. At least twice for every cycle. So the question is, how many times must I read this conversation? In other words, how many times must this switch be in position A per second? Well, that depends on the highest frequency. Yes. We take the highest frequency, not the lowest, because remember every cycle, even at the highest. So we take the highest frequency of 3,600 Hz. Let's say this is it here. Right. for example, then we must at least sample it twice during the sometime during the cycle. It doesn't matter which two positions we take. It doesn't matter as long as we do it twice in one cycle. We can do it more than twice, but no less than twice. So the number of times I need to sample would be twice this. So it would be 3,600 multiplied by 2. So you're going to talk about 7,200 times. Let's say we do it a little more than that, which is no problem. Let's say 8,000 times. 8,000 samples per second. Now what that means in practice is that this switch has to rotate 8,000 times per second, doesn't it? Right. Now you can see a mechanical switch wouldn't work. We have to do this electronically. But the principle is the same. Mechanically, it would be rotating. Electronically, it would be done by using gates and things like that in logic circuits. But the idea is this. It's still the same whether we use mechanics or not. It must rotate 8,000 times every second. So if we take any one of these channels, let's say channel A, then 8,000 times per second it takes a little sample of the voltage, sends it over to here. This is in the same position A, and shoots that out to the receiving speaker. And same with B, same with C, same with D. Now basically what's going along here, right, if we have a look what's going along here, we get a funny waveform here. We're going to get a lot of little voltages, right, all of different amplitudes. Some are going to be bigger, some are going to be smaller, some might even be negative. Yes, depending on exactly what the signal is at that instant when it contacts that point. Okay, so that's what's going to happen. Now, in my example here, I said we're going to rotate the switch 8,000 times per second.
Yes.
And in my example, we've got 1, 2, 3, 4 channels.
Times
30.
Right, so the actual time, like this would be channel 1, or channel A. Then we take a sample from B, which is slightly different.
32,000.
Yeah.
32,000.
Sample C and then sample D. And then we go back to A again. It's gone a complete revolution, hasn't it? A, then B, then C, and then D, and so on and so forth. So it goes A, B, C, D, A, B, C, D. And you can work out how fast it has to rotate, or how fast, or how small, shall I say, these little pulses are, okay, depending on how many channels you have. For instance, if I have 4 channels and 8,000 samples per second, then this must be 4 times 8, 32,000 per second, isn't it? 4,000 pulses per second. Sorry, 32,000 pulses per second. Let me just put this down here. Pulses per second.
For each
That is for the...
full channel.
Yes, that is for 4 channels. Now, of course, if I have more channels, I'll need more pulses, won't I? But it's as though we've got all the channels in the one spectrum. Each little pulse represents a small sample from each of the channels.
But it will be continued that you will hear the voice. That can be
Yes, basically, if everything works according to plan, what you hear out of this speaker will only be what's spoken from here, because there's 2 switches are only in that position at that instant during the transmission of that pulse. Then they move to B, so we're now on the next pulse, and only what's spoken here will be heard at B, and only what's spoken at C will be heard here, and so on. So channel A will not be able to hear anything from channel B. Channel D won't be able to hear anything from any of the other channels, and so on. They are separate channels. But they're not separated by frequency, they're separated by time. This is called time division multiplexing.
About that, this one rotating, and that one...
In rotating,
1 channel to receive.
1 channel to receive, 1 channel to transmit. Okay, so this is
Same channel.
Sorry?
The same channel.
That's right. When that's in A, that's in A.
With the channel the receiver.
That's right. They must be synchronized. They must rotate at the same time. When that's in B, that's in B.
Yeah.
That's in C, that's in C.
It is very
Very fast, 8,000 times per second.
One channel is 80,000.
Yes, every channel
Every channel.
has got to have 8,000 samples per second. So the number of pulses
4 channels.
travelling down here
Multiplier
would be
for-
4 times 8,000, wouldn't it? Because for one rotation of this, we're taking 4 pulses. One from
32.
here, one from there, one from there, one from there.
32,000.
That's right. 4 pulses per rotation. So if this is rotating 8,000 times per second, then the total number of pulses
30,000.
will be 32,000 in this example. Now that's a common figure, by the way, for TDM. 8,000 samples per second for telephone work is a common figure, so I'd like to remember that. But this particular type of modulation that we're using here, right, is actually a type of pulse, what they call pulse amplitude modulation. Because each of these pulses has a different amplitude, doesn't it?
Yes.
Some are high, some are low. Type of analog signal, but the type of modulation is called pulse amplitude modulation in this TDM circuit. Now, pulse amplitude modulation isn't the only type of modulation that's used in TDMs, but this is the easiest one to understand to begin with. PAM, pulse amplitude modulation. The other type we're going to cover when we do data comms. I'm not going to cover the...
what is the other case?
No, the other type is PCM, pulse code modulation. Okay. And we're going to do that in data comms. We're not going to do that in this section of the course. Just going to do the pulse amplitude modulation. We can draw maybe a better little diagram than that if I draw something like this. So, this would be A, B, C, D, and then again A, B, C, D, A, and so on and so forth. Now if we just have a look at channel A for a moment, and right, what's coming out of channel A will be just this pulse, and then we get nothing until we get another
Yes.
pulse for channel A, do we?
But the frequency between them.
That's right. Basically, that's all we need actually to build up, and then we have another one here.
You mean
So this would be A.
adding mini channel?
Yeah, well,
One,
yeah, basically, what you actually receive here, right, is just what's for channel A, what's coming from channel A.
Can you say it's similar like auto modulation?
It is like it is modulated. In other words, if what you would have a little filter here actually,
Yeah,
like an integrator, which would actually smooth these out
yeah.
and give you your original audio signal. That's the idea.
Similar like carrier, similar like carrier the A.
Well, I haven't actually mentioned carrier as such here because it's like channels, exactly the same, but the channels are separated in time, not in frequency.
Yes.
That's the difference, separating in time. So we can get our original audio signal from this speaker, from this somebody speaking into this microphone here for channel A.
Yeah.
And then B the same, C the same, D the same. They all work exactly the same way.
Can we calculate the frequency for each channel? Maybe.
You can. If you knew how many pulses per second, then you can calculate the frequency of the pulses here. Right? But of course it depends what sort of information you're sending. Again, for this example, I'm using telephone as an example. So we're talking about a maximum of 3,600 hertz. So we need about and this is a standard figure, they usually use 8,000 samples per second per channel.
And we have here 8 channels.
In here, 4 channels.
No, I'm saying
Sorry, it's
about,
30.
about A now. I want to know the frequency.
Right. If we're taking 8,000 samples per second, then the time difference between here and here
Yes.
is 1/8,000th of a second, isn't it? You can work that out in milliseconds if you wish.
You said that the minimum frequency or the minimum gating time is twice the maximum frequency.
Yes, that's right. Yes, it should be.
To achieve what exactly?
Well, it's called the Nyquist law.
What's that?
Nyquist. Have you heard of Nyquist?
No.
Okay. Well, Nyquist is the name of a guy who did experiments and all this. Again, but what he said basically was this.
It is not necessary to send
No.
all
Right. You don't need the whole wave to reproduce it. That's basically it. What he said was, if you take a single frequency, single wave, sine wave, he said, if he showed you just 2 values of voltage, any 2 values, no matter what 2 value, where they are, 2 values of voltage during this period, you can reproduce that cycle. You can't do it on 1, but you can do it on 2. You can reproduce that wave. That's what he says. And we have to take his word for it. But if you must have, for instance, you could have 1 here and 1 here, if you wanted to. And you can reproduce the sine wave. That's what he says. At least 2. If you have more, so much the better. You can reproduce it even better. But 2 samples is all you need to reproduce the original sine wave. So, if we're producing a band of frequencies from 300 to 3,600, then we take the highest frequency, 3,600, and we say we must at least take 2 samples during that time, which is 7,200 samples per second. The standard for radio telephones is 8,000 samples per second. That's the standard. So that's the reason why I want you to remember that.
But you take 2 highest frequencies.
You must take the highest frequencies,
But now
yes.
the circuit is looking so that how can I know the minimum?
The minimum, if you take the minimum frequency, if this is the highest frequency, then the minimum frequency will be a lot longer, won't it? And if we take the same number of samples that we're using for the high frequency as for the low frequency, which is what we do, then for the lower frequency, we're taking a lot more samples within the wave. So it works even better for lower frequencies. So it's the highest frequency that's the critical one. You take the highest frequency you're going to transmit, multiply it by 2, and that's the maximum number of samples. There is a little note in the handouts I've given you on this as well,
But
about PAM, pulse amplitude modulation. Switched off all this time. Now, of course, as I said, in practice, physical switches are not going to be used because you're going to have to rotate too fast. But you can see some of the points about TDM. First of all, one of the points is, obviously, we need some electronic switching, not mechanical switching to do this. The second point about it is we need to be able to switch fast enough to give me 8,000, at least 8,000 samples per channel, if they're telephone channels. What about if it was a television channel? Yeah, you're going to have to go much higher than 8,000, aren't you, because of the bandwidth.
6 meg.
Yeah, well, if a TV channel, say, 5 meg, then we need at least 10. Remember twice the highest frequency?
Yeah,
10.
to take a good picture, you need like 20.
Yeah, I mean, you're talking about very fast indeed.
So that now you have taken three kind of modulation.
Yes, PAM. This is an example of pulse amplitude modulation.
And we have completed frequency.
We did
frequency modulation.
and amplitude modulation.
And now the type of multiplexing, it is frequency division multiplexing.
And time division multiplexing, yes. Exactly. Now, let me give you a practical example of where they use this, for those of you who don't know. In the airport and in our mobile radio system, we have what are known as voice recorders, don't we? Faisal, you're the expert. Keep it on here. You don't want to look at me. Voice recorders. What do we use voice recorders for? You explain to the class why we use voice recorders.
Because there is important message coming from different departments.
Right.
To make the what is called the traveling and the communication easier, to make the access time almost minimum for the airplane traveling. So that it's important to receive all the messages and record it.
It is important to receive all the messages and record them, but I wasn't sure why in your explanation as to why that was the case. Let me give my explanation and see if you agree. What we're doing, we're recording all the conversations on our mobile walkie-talkies around the airport. Okay? Why are we doing it? Basically, in case somebody wants to check some history. For instance, if something goes wrong,
Yes, something, accident.
if an accident happened, they need to find out who was it who gave the order,
Blame who?
blame whom,
Like in the black box of the...
like a black box recorder, exactly. Very similar, except recording voice.
Investigation.
Like if somebody, when we first put out the trunking system, started to use bad language over the
Yes.
system. So they need to find out who, I don't know if they ever did, but they...
The bad language, it is overcome by the because before everybody they transmit and we don't know whom.
That's right. Trunking is a bit more difficult to do with that. But it is still possible. So what it does, you have a recorder, just like a tape recorder, that records what's going on, but it has a different channel for each radio channel. Right? Now, imagine here, instead of 4 of these, you have 16 channels. Right, so everything's obviously much faster. 16 channels. And what it does, it samples each of the 16 channels 8,000 times per second, just the same as this. Right, but it obviously gives a much higher pulse rate, doesn't it?
480,000.
Right, yeah, if you multiply, okay then. 480,000 pulses per second, isn't it? Each one a different amplitude representing that channel. Now, what it does in the voice recorder, they then record this. Instead of sending it to somebody else, they record it on tape. And they record it on VHS videotape. But it's not video, it's audio. They're not using it for video, but they're using it for audio. They record it on VHS tape.
Because when you say
In
that...
Royal Coms we have like this.
That's right, exactly.
It's called record.
It's called the Rockwell Voice Safe,
What's it?
Word Safe.
I think the work of the... I see the tape of the video like this. The lines like this inside you put it in the light or I see it in some box.
Oh yeah.
I see the tape of the video, they show it like this, like a way, like the cinema channel.
Channels.
Maybe high frequency for it.
Well, although they're using videotape,
Yes.
they're not actually recording video, they're only recording sound, but they're recording sound from many channels altogether. And it runs quite slowly. Has to be changed every 24 hours or something, the tapes. So that's one example of the use of PAM.
The modulation the same time. It's one.
Yes, it's using exactly this principle.
The same, but different. The time different to take the negative and the positive.
Yes, that's right. It's using the whole wave, of course, and also 16 channels instead of 4, so it's much faster.
for the time division,
Yes.
and the pulse amplitude the same.
Well, whatever the amplitude is at the instant, that's the amplitude of the pulse. It is still pulse amplitude modulation,
Yes,
and it's using time division multiplexing,
yes.
right? But it's only for audio, recording 16 audio channels.
So I'm talking about the old model for Rakam. It is, you know, that one, it is detailed.
64 channels.
It's 64 channels, is it? Yeah, but I think what they do there, they use a different track. In other words, there's a different set of switches for another 16 and so on. So they use 4 tracks.
Channel for radio, channel for silver also.
For, yes, that's right, yeah. As long as it's audio. Any audio channel, it doesn't have to be radio, any audio channel.
Air traffic control.
They will have they'll have the same, exactly the same system. Because if there's an accident, they need to know what was said, what was...
The pulse amplitude modulation, the maximum channel they use 16.
No, I only gave that as an example. I'm not quite sure. I think in the word say they use 16 channels, and then they use... see, this would be recorded on one track on the tape, but they have many tracks. Tracks or channels, not to get the confusion. And they have more than one track, you see, so they can get 64, I think, is it? Maximum number of channels.
So the pulse amplitude modulation is a kind of time division modulation, or what exactly?
Pulse amplitude modulation is a type of modulation
Yes.
where we send pulses instead of a continuous wave. This is not radio now.
Yes.
And the amplitude of each pulse varies, okay, depending on the signal that you're sending. Now, the question is, why do we do that? And the answer is, it's basically to fit in for time division multiplexing. If you understand what we did here, you can see why each of these pulses is a different amplitude from each of the channels. So really, one goes with the other.
Like different frequency in frequency division.
Yes, instead of using a different frequency for each channel, which we would use in FDM, we use what we call a different time slot. Like A takes up this time slot here. Like channel A, if I was to colour it differently, this is channel A, isn't it?
One is different.
So that's channel A time slot, right? Channel B time slots here, and so on. They're time slots. This is not frequency, this is time.
Yes, that.
See? Whereas the other graph was frequency, this is time.
But this time we deal by amplitude, not by frequency.
You got good news and I got bad news.
Oh, I don't like these good news, bad news. Remember the joke? There's a guy who between two limits. So that's the other point about PAM that we need to mention. Apart from that, I'm not going to speak much more about it, just to introduce you to these words and basically what they mean, so that you know, you can't say you've not heard that before. You know, pulse amplitude modulation, time division. Now, we'll be coming back to this subject again when we do datacoms. We'll be doing it, but we won't be talking about PAM in datacoms. We'll be talking about something called PCM. PCM, which is pulse code modulation. And we'll talk about it again as a separate thing. But that's datacoms, and we'll be doing that, you know, when we do datacoms. Okay, so any questions about this? Everybody's happy with this idea? It's just a concept, just an idea. I want you to get into your mind what we mean by this, so that you have, you know, you've heard about it.
Each channel offer one band.
Yes, basically, like here, I've drawn one line here. Now that could be a cable, electrical cable, or it could be a single channel of radio.
One at a time.
Yes, basically, that's exactly what you're doing. You're taking a little bit, one at a time, in fast order, from each channel,
At the same time.
and sending it down, well, they're called time slots, right, along the same media. Right. This could be a cable, it could be anything. Right? That's what's happening. Okay,
هلا علي.
there he is. Here's the good news. Morning.
Sorry for that.
You've had some problems. Maybe you can copy the notes off somebody else that we talked about here. This will be, this is mainly the thing we covered anyway that you missed. Now there's only really one other subject I need to talk about as far as telecoms is concerned, and that is the optical fiber communication system, which is relatively new, particularly here, but it's not a new period.
You don't use analog or digital, use light.
Well, we can still talk about analog and digital signals, but it uses light as the media, right? And instead of using radio frequencies that we know, it uses light frequencies, but it's still electromagnetic. Okay. Well, before we talk about that, shall I erase this now? Everybody got this down? Okay. Let's get rid of this and let's just talk about.
أصحاب طيبين زي حيز.
Okay, now fiber optics. How do they work and what's happening here? You all know how a conductor works in transmitting information. We produce an electrical signal, connect it to a copper wire, for example, and the current will flow through that copper wire, producing an electrical signal, so we can get distant communication by that means. Well, with fiber optic communication, what we use is light waves. Yeah. Now, if you remember what we've talked about, light waves are a type of electromagnetic wave, just the same as radio waves are, but they're much higher frequency, aren't they?
Yes.
And indeed, because they're higher frequency, they have much shorter wavelengths. Okay. Okay, we'll come back to that question of frequency in a minute. But basically, what's happening with fiber optics, what we do is we have a source of light. I'll just draw a little box here and assume there's a light coming out of it. And then we have a cable, and I'm going to talk about the cable in a minute, that takes that light down to some distant point. Now, how the cable works is interesting. So if I shine the light at this end of the cable, the light should come out there. Okay? How the cable works is interesting. Basically, it's made of glass. Actually, some cheaper ones can be made of certain types of plastic, but the original ones are made of glass. And if I was to magnify the view of this cable, what it looks like is two pieces of glass. First of all, we have a glass rod, like that, and then around the glass rod, we have a glass cylinder. The difference between this glass and the outer glass is its reflection. What do they call it? The amount of reflection that it has, or diffraction of the light. What happens is this. If I was to draw this in a different form like this, this is the rod in the middle. This is the tube on the outside of the rod. When I shine light into the rod, then what happens is the light spreads out like this, then it hits this glass, which is a different reflection rate than the inner tube, and therefore gets diffracted and bent back in again towards the center rod. And this continues to go on throughout the length of the rod. So the glass causes the light to remain within the fibre. The fibre is actually two pieces of glass.
But it is not reflecting inside the second glass.
It goes into the second glass and then back reflected back down again. You know, I remember when we spoke about the ionosphere on HF, the wave goes up and it's bent by the ionosphere, bent back down. Very similar thing. Only of course here,
Short
the
wave.
frequencies are much, much shorter.
Yes.
That's right. Even shorter than, of course, the radio frequencies, because we're talking about micrometers here of wavelength. And depending on the type of glass that's used, and of course this is a study in itself, then the light will be retained within the glass tube. Okay? Now, of course, the actual thickness of this is very small indeed, just a few millimeters, in fact, a fraction of a millimeter thick. It's like a fibre, just a little bit thicker than a hair, human hair. It's a little bit thicker than that. Inside it, though, is contained two parts, as it were, to the glass fibre. The inner part, which is a rod of glass, and an outer part, which is a tube of glass. One is inside the other. The idea being that any light that's shining here will be reflected backwards and forwards and will travel down the tube. Even if you were to make the rod flexible, you know, the cable flexible, the light will travel down it to the end without any losses, without it coming out of the sides. The idea being that the light energy we put in here comes out here. It's quite efficient. Yes.
I don't know, but the way we learn this one is that it's not getting out of it. The same body of the fiber from inside.
Yes.
The same body is acting as a mirror.
This is, yeah, this part here is acting as the mirror.
No, the inner one.
Yes, but it has to, yeah.
Every rod. If there was no any outer piece of glass, if it was only one piece of glass,
Mhm.
and you applied any light,
Mm-hmm.
the source, it would hit inside.
Yes, but okay, well, what you're saying is then you're using something else to refract, maybe the air or something like that. But there's got to be something here which is different, a different reflection than this, in order to bend the light back.
There was also an experiment to show this. The theory is to bring an aquarium of water
Mm-hmm.
and apply the light and bend it until the light is hitting up.
Yes.
You see the beam hitting the other way.
Oh, yes. The whole idea is this. For instance, I mean, you can even see this if you have a tank of water, imagine. You know, if you have a large container of water. If you put a stick or a pencil in the water, when you look at the pencil looks as though it's bent. It appears to be bent. The reason is because when light travels between two